In this video, we'll talk about an intrinsic semiconductor. Let's begin by looking at a silicon atom. A silicon atom contains 14 protons, 14 neutrons, and 14 electrons. Among these electrons, 4 are valence electrons, which participate in covalent bonding. When many silicon atoms are placed closely together, they form a bulk silicon crystal. But how does this bulk silicon look structurally? Let's first think about carbon. Carbon has 6 protons, 6 neutrons, and 6 electrons. 4 electrons are valence electrons. Carbon atoms also form covalent bonds, and a famous example is the diamond structure, a 3D repeating lattice. In a similar way, pure silicon also form a diamond cubic lattice crystal structure. Here you can see the unit cell of silicon. A unit cell is the smallest repeated unit that builds up the entire crystal. In this diagram, the sphere represents silicon atoms and the sticks represent covalent bonds, each made from a shared pair of electrons. Now, will all electrons form covalent bonds? At absolute zero, say T equal to 0 Kelvin, yes, all valence electrons are tightly bound in covalent bonds. However, at room temperature, about 300 Kelvin, thermal energy allows some electrons to break free from the bonds. These freed electrons can now move throughout the crystal. So by thermal energy, electrons pop out from the bond and move nearly free. When an electron breaks away, it leaves an empty space in the bond. This absence behaves like a particle and can move as well. We call this imaginary positively charged particle a hole. A hole effectively carries a plus E charge, where E is the elementary charge. In intrinsic silicon, electrons in holes are always generated in pairs, a process known as EHP, electron hole pair generation. Let's now apply an electric field across the silicon. Electrons, which are negatively charged, move toward the positive terminal. So electrons will move to this way, and holes with effective positive charge move toward the negative terminal. So the holes will move to this way. As a result, both contribute to the electric current, and the net current direction is from positive plate to the negative plate. So this will be the total current. We can describe the current more quantitatively using current density, J equals to N Q mu N E plus P Q mu P E, where N is the electron concentration and the unit is number per cubic centimeter, and P is also equals to hole concentration, and mu N and mu P are mobilities. And of course, E is an electric field. In intrinsic semiconductors, both N and P are very small, so it is approximately 0, or compared to other things, it is very small, so J is close to 0. This is why pure silicon has very low conductivity. And by the way, conductivity is to J equal to sigma E, so the conductivity sigma is defined as NQ mu N plus PQ mu P. However, we can drastically increase conductivity by increasing N or P. And this process is called doping. So doping can increase N or P. So this conductivity sigma can be modified. In, in the next video, we'll discuss doping and how it improves semiconductor performance. Thanks for watching.